In this video, I'm going to walk through how to conduct an investigation using the PhET circuit lab to determine the internal resistance of a 6-volt battery using the graphical method. So the first thing I'm going to do is set up my equipment. I have a battery and a resistor. I need an ammeter to measure the current that's passing through the resistor and the circuit, and I need a voltmeter to measure the voltage across the load resistor. So I want to set my voltage at 6 volts, and I'm going to set my resistance at a range. Now I have between 0 and 120 ohms to choose from. So starting at 10 ohms and maybe going up by 10 ohms each time, which will give me a good range. The other thing I need to do is to set the battery resistance. I want a low resistance or a low internal resistance. Now, in reality, we can't set an internal resistance. It's just a property that batteries have, and that's dependent on age, the type of battery, the size, and so forth. So doing a virtual investigation, we need to model this part of the process. I'm going to set it at, say, 2 ohms or maybe 3. I might set it at 3. So this actually gives me a value that I can compare the gradient of my graph. When I do my graph, the gradient should actually equal the internal resistance, so it should equal 3 ohms if it's done correctly. So I'll just hide that now. So it's like I don't know what the internal resistance is. I have to measure it. So I'm just going to check my values. 6 volt battery, 3 ohm internal resistance, starting resistor 10 ohms. I've got my current in place. I'm going to take a screenshot of that and put it in my report. So now I'm ready to start thinking about my method to step that through. In my method, I need to be able to indicate the variables that I'm changing, the variables that I'm keeping the same, and the variables that I'm measuring. So that needs to be explicit or implicit in my method. So I'm going to consider my battery, the 6-volt battery, as being a constant, but I'm not going to consider the internal resistance as a constant because it's the property that I'm trying to measure. In a real battery, we don't set this. We can't control it. So it's a thing that I'm trying to determine using the graphical method. The variable that I'm changing, or the independent variable, is the resistance of the load resistor. What I'm measuring is the voltage across the load resistor and how that changes dependent upon the size of the resistor. So I've just provided a bit more detail to describe my experimental setup to show I've got my 6-volt battery, a starting resistor of 10 ohms, an ammeter in series, and a voltmeter in parallel to measure the voltage across the load resistor. So the first step would be to measure the current through the resistor and the voltage across the resistor. And obviously I also need to record this information. The next step would be to increase my resistor by 10 and repeat and do the same thing again. And I want to continue doing that until I've reached the maximum resistance available, which is 120 ohms. Okay, I think that does it. Now to design a table for us to record our information. So here's where we'll go into our Google Sheets to create a spreadsheet that we can then use to graph the results. We need to think about the headings. So we've got a changing resistor size, so we need to include that. Then we need to include the current because we want that on our x-axis, and then we want to have the voltage across. Where do I get the symbol for ohms? Well, I need to do a bit of a trick here because we don't have the option of including special characters. So I use the Google document to get the special characters. So insert special character, I can just type in ohm and here's my symbol here. Then I can just copy that or cut and paste into here like so. All right. I want to do text wrapping. So I select this information here. I go format, text wrapping, wrap text. And then I want to center it. Okay. And then maybe bold it. Okay. So that's how we do that. So with the headings, we need to be specific. We are talking about current through the load resistor. And we're also talking about voltage across the load resistor. We need to say that explicitly. There's one piece of information I did actually forget. So I'm going to come back here and I'm going to disconnect my battery because I want to measure the open circuit voltage of my battery. So this is the voltage that it would supply without a load. It says 6 volts because there's no circuit attached to it. That's the voltage available, but once it gets connected, then that's when the internal resistance is going to take effect. So I need to record that value here. Obviously, if you buy a commercial battery, it says it's 1.5 volts. When you measure the open circuit voltage, it won't be 1.5, or it's likely to be more or a little bit less. So again, our simulation doesn't model reality perfectly. So I'm going to come back here and insert that step. And actually, again, I want to measure and record. This value here, the open circuit voltage from the presentation, it was explained that that will be where the line passes through the vertical or the y-axis. So that will give us an indication of how accurate our measurements were as well. If that crosses through at 6 volts, and if we end up getting a gradient that gives us 3 ohms, which is what we've set the internal resistance of the battery. So if those two agree, it's pretty good indication that it was done accurately and that our investigation was valid, that we managed to control all variables. So back to my investigation. I'm going to type in my resistances. So 10, 20. Remember the trick, if I type those first two, I click and drag to select the 2 cells. I point towards this little box in the bottom right corner, turns into a cross. Then I can drag it down, let go, delete that last one. So I want it from 10 through to 120 ohms. Now I might put a line around the table. Okay, I want to record somewhere my open circuit voltage. So I need a value here somewhere. I'll just call it VOC and it measured at 6 volts. Okay, so if I put here my units so I know, because you always need to say what the measurement is and what the units are. So I've got 6.0, so let me increase my decimal spaces. All right, I might frame that as well. Okay, and then I have a value here I can compare it to. I probably should put my internal resistance. Remember, in reality, we won't know what this is, so, and I should be able to do that. Okay, good to go. So I'm going to take some measurements and fill in my table, and then we'll come back and do the graph. Now, again, before I start, because I've played around with the circuit, I just want to check my values are all good. Yes, 6 volts, 3 ohms, 10 ohm load resistor, good to go. I'll take my first measurement, close the circuit, 0.46, 4.62. enter it and double check that you get your measurements correct. You'll know if you've made a typo because you'll get an outlier. So now I'll come back, I'll increase this to 20 and repeat. So 0.26 and 5.22. Okay, so now having completed the data, when I look at it, when it gets up to the higher resistances, we have a bit of a problem here because it's only reporting the 2 decimal places. So, that sort of would be a trigger for me to probably not have it go up as high as that if I can't measure beyond the 2 decimal places. But anyway, we can continue with that and see how it looks. So I'm going to do a graph of voltage across the load resistors versus current. So I'm going to select those 2 columns, including the headings, and do a scatter graph. Okay, so it's done a line chart, which I don't want because I need a scatter graph so I can plot the values and fit a trend line to that. So let's go in and make some adjustments. So go into customize. First thing I do is go to series and I change my circle to cross marks. While I'm here, I'll do my trend line. While I'm here, I shall include my equation as the label, which gives me lots of good information, which is exactly what I was hoping for, because we look at the equation, it's telling us the gradient is 2.99, which is pretty close to 3. If we round it, it'll give us 3. Where it crosses the vertical axis is 6, which matches exactly to our open circuit voltage, so that's good. I want to make sure that my horizontal axis goes to 0, so I need to, since see that, I selected that and it goes straight to where I want it. There you go. So I just changed that to 0. Okay, I want to increase that because we don't like to have our lines just going up to the highest value, so I want to make it above that, so I'll probably set that to 8. So if I click on this vertical axis, it gives me the values here. I'm going to just include my 0 and I'm going to make it 8 and see how that looks. Okay, that's quite better. And here again, I think I'll make that a maximum of 0.5. Perfect. Okay, so I like to include grid lines. So I'm going to, if that goes up by 10, goes up by 0.10, I want maybe to go up 2, 4, 6, 8, 10. So minor grids I might make 4, so that means 0.2, 0.4, 0.6, 0.8, 0.10, and I could do something similar here, I guess. If I do 9, then that means it goes up by 0.2, 0.2, 0.4, 0.6, 0.8, 1. Yeah. Okay, and that's pretty much it. I will change my heading. I like this. I will change my heading. I can actually click and type it straight in there, and call it internal resistance of a 6-volt battery. And that's it. So I'm going to copy this into my report, include a new page, and I will link it to the spreadsheet. And to copy this, now there's no option in the right click, I just have to select it on my keyboard, go Control C, and then come back and go Control V, and I can again say yes, link it to the spreadsheet. So in the results, I tend to not like to just dump in a table of results without sort of introducing it. So I usually do a brief blurb to say, here's my results in the table, for example. Just a nice simple sentence. That's it. Okay, so let's write a discussion and conclusion. In my discussion, I don't want to just write general comments. I want to give explicit information. I'm going to evaluate and I want to make a claim about accuracy, validity, reliability, and base that on evidence and be explicit about that evidence and then give reasoning for it. And my main discussion is going to center around the graph and compare that to this information here. So the first thing I'm doing is describing the graph that I plotted the voltage across the load resistor against the current through, that it produced a linear trend line which had an equation of this. Okay, now I'm going to interpret what this is. So reading the equation, I'm saying that the results showed that the internal resistance is 2.99 ohms and the open circuit voltage is 6 volts. Now I can just add a little bit of detail to say that I can relate this to the graph. Okay, so I've just added that the gradient is 2.99 and that the 6 volts is where the trend line crosses the y-axis. Okay, so that links it to the graph and to the equation for the straight line. As we know, the general form is y equals mx plus b. I'll do a really brief evaluation of accuracy, reliability and validity, which would be done quite differently when we're doing the real investigation. In terms of reliability, using this virtual lab, there's no point in repeating because it's going to consistently give us the same values. I don't think there's going to be much random error, if any, but in reality there will be. So that's when we do it in the lab, we'll actually repeat these and be able to compare the values to each other and to an average. But I guess we can look at the graph and look at the plots, and the plots are fitting exactly on the line. So we would say there's no random errors going on here. It's pretty reliable. In fact, it's pretty much perfectly reliable, only because it's a simulation. Okay. In terms of accuracy, well, accuracy is determined by how close your measured value is to what's expected. Well, we manually set the internal resistance to 3 ohms, which is something you can't do in reality, but we have a known value in this case that we can compare our experimental value to. The experimental value was 2.99, rounded up, it'll give us 3.0, so that's pretty high accuracy. Okay, the other thing that we can compare is the voltage. Now we actually at the start of the investigation, and something we will do when we do the actual investigation, is we measured the open circuit voltage beforehand. It gave a measurement of 6.0 volts. Our line where it crosses the y-axis was pretty much on 6. So again, that's indicating that we've got accurate results, and also our investigation is valid. We were able to control any variables to produce a valid investigation. So I'm just going to summarize all that here. So here's my brief statement about reliability. I've made a claim that it's highly reliable. I've given my evidence that the plotted values fit perfectly to the trend line, and I've added a bit of reasoning here in terms that because the investigation was done using an online simulator, there are no random errors affecting the measurements. And I just added, so if the investigation was repeated, the values will be concordant. So that's suggesting that these values will be the same. So there's no point really doing it again. In terms of accuracy, I'm making a claim that it's highly accurate, and I'm giving evidence that I'm showing the measured value and I'm comparing it to the known value, which was manually set in the simulation. Again, we can't do that in reality, so making a claim towards accuracy when we do it, we can only make a suggestion that it's, if everything else, if the investigation was valid and we get a value, we can suggest that that value is a good estimate of accuracy rather than saying how accurate it actually is, because we won't know what the true value is. And my last brief comment about the validity. So I'm making a claim that the investigation is valid. And in this comment, I'm saying what I'm using to judge validity in terms of variables being controlled. And the evidence that they have been is that the open circuit voltage that was measured where the trend line crossed the y-axis, well, that's exactly as was expected, because we set the battery to 6 volts, and before we connected it, we measured the open circuit voltage. So now I'll just finish with a conclusion. So I'm just going to refer back to what was the aim of the investigation. So I'll start with this. The aim of this virtual investigation was to determine the internal resistance of a 6-volt battery using the graphical method. And then I'm just going to briefly say what my results were, and that's pretty much it. So I've made my statement about restating what the results were and that it agrees with the expected value. But in reality, we don't know what the expected value will be. So we will deal with that in a different way. And that's it.